So let's start from just few bio notes. I have a background in electronic engineering. I did my bachelor and my master at University of Calabria in the south of Italy between 2013 and 2019. And then in the same university, I did my PhD in information and communication technologies from 2019 to 2023. During my PhD, especially in the last year, I was also a visiting student here in Edinburgh at Heriot-Watt University. And overall, during the PhD, I worked on design methodologies for FPGA-based deep learning accelerators and their characterization. After that, I moved definitely to Edinburgh for working, starting as a postdoctoral research associate in embedded system design here at the Center for Electronics Frontiers. And in the same center, I moved as research fellow in AI for circuit and system design automation in December, being part of the April AI Hub at the University of Edinburgh. So now let's go to the specific topics of today's talk. So let's start with some basics about convolutional neural network. I would start from a relationship that we have between convolutional neural network and our brain in order to highlight what are the biological insights on the use of convolutional neural network. So, like our brain, where actually deeper region handle more abstract information, the convolutional neural network learns simple to complex features as data flow to their layers. And in order to understand this, we might consider the example of the object recognition in an image, no? So our eyes are able to detect an image through the retina, that is the very first layer that behaves as a sort of imager. And basically, the information grabbed from the retina is moved to the lateral geniculate nucleus, the LGN, that is a sort of relay between the retina activity and the visual cortex activity. In the visual cortex, that as you can see, it starts from the occipital side of the brain, we start the pattern recognition in order to understand the specific object that is contained in our image. We have different levels of visual cortex that are responsible to extract the piece of information at different level of abstraction and complexity. So let's say we start from very simple edges underlining the objects, and then we compose the more complex object, the colors that are involved in the image, and so on. So we move deeply inside our brain and we reach the inferotemporal cortex that is responsible for the final classification of the object. As an example, in this figure, we have a cat in the object, and so through different layers, as highlighted in the top image, representing the brain, we are able to identify the specific object, in this case, the cat. So this is, let's say, the biological relationship of convolutional neural network with our brain visual system. Now, where convolutional neural networks sit in the widespread AI landscape. So basically, we start from artificial intelligence that merge science and engineering to build intelligent machine. Then we move internally to the machine learning. So basically with the objective to build machine that are able to learn without being explicitly programmed. And then inside the machine learning field, we are able to move into the brain-inspired computing, and so neural networks that basically mimic the behavior of our neurons to, let's say, build knowledge starting from the input data. And obviously, very complex neural network consisting of many neurons arranged in wide layers belong to the deep learning field. Inside the deep learning field, we have the convolutional neural network that, as I was explaining before, take inspiration from the human visual system to extract patterns, information from the images. So, convolutional neural network find wide applicability in many fields. In this slide, I've just collected very few insights about three major areas. So we have computer vision, autonomous systems, and other stuff. In the computer vision, we have image classification, image segmentation, that is basically a pixel level classification. So basically we label each pixel of an image with a specific class. Face recognition, medical imaging, and satellite imaging. Moving into more complex stuff like autonomous system, we might exploit convolutional neural network in vehicles and in robots. According to vehicles, we can exploit CNN for lane detection, traffic sign recognition, and according to robots, we might exploit CNNs for path planning and object detection. And finally, we might still exploit those architecture for time series analysis, recommendation system, drug discovery, style transfer, and defect detection. Obviously, this is a not exhaustive list. I've collected just, let's say, very interesting and well-known application that make use of convolutions. But now I would say it's proper to provide a bit of background on how the convolutional neural network works before moving into the potential hardware implementation of this type of neural network models. So basically, the key computation that stay at the convolutional neural network level is the convolution itself. So basically, the role of the convolution is to basically use a kernel that is basically a filter that scan the image in order to extract a proper piece of information. So now the convolution concept is quite, let's say, old because it was applied originally in conventional image vision application. As an example, the detection of edges in an image. So using fixed wave to understand what are the borders between an object and the other, let's say the Sobel filters. And starting from this, it got a lot of attention to actually being employed in learning stuff. So make these filters, this kernel, able to be configured during multiple iteration in order to fit the specific type of object and feature that should be detected from the images. Now, these kernels scan the image in a raster order. So we scan from the top to the bottom and from the left to the right. The key type of operation that the kernel executes with the image, that is called feature map, is multiply accumulation. So a series of multiplication and accumulation between all the products. As a final note, the weights that basically compose the kernel that you see in yellow are shared at the input feature map level. It means that this yellow box, and this other yellow box contain the same weights. In particular, here we have a 3x3 kernel, okay? Now, just to understand the mathematics behind, I have considered a 3x3 kernel with weights from A to I, and a 5x5 input feature map from activation or pixel between 1 and 25. So basically, if we start from the top left, the first windows is this, and basically the first operation is highlighted by the orange box, 1 by A, plus 2 by B, plus 3 by C, and so on. Then, after this filtering that provides the OWA1 result, contained in this position in the output feature map, the kernel move of one position, and this step of difference between the first kernel and the second kernel is called stride, and move one position and perform another convolution, with the computation reported in the yellow box, so providing the results O1, 2. At the third step, we have the third kernel, with the computation reported in the green box, and then we move the kernel and the next row, so the activation 6, 7, 8, 11, 12, 13, and 16, 17, 18, performing the convolution with the kernel, and so on till the completion of the image. So this just to recall the concept, the mathematical concept behind the convolutions. Now, in convolutional neural network, as we were discussing at the beginning when we were highlighting the relationship with the biology, we said there are multiple stages that are responsible to extract knowledge at different level of abstraction. And the sort of computation that we described here, so the convolution between one kernel and one feature map, extend in a sort of three-dimensional space. So we have multiple two-dimensional convolution between different kernels, and the result of each convolution are accumulated into the space, in particular into the channel axis, in order to get the results that compose the final output feature map. So basically, we might consider convolutional layers as scaled architecture in the space of the basic convolution computation, where still we perform multiply accumulation, but there is an extra source of accumulation in this space. Okay. Now, the set of input that compose the generic convolution layer are called input feature map. We have different channels of input feature map, and each channel consider distinct k by k filter. Now, the kernel can be 3 by 3, 5 by 5, 7 by 7, 11 by 11. Generally, what it is very common is to use small kernel sizes in order to build a very strong relationship between the close neighborhood of the input feature map activation. But we have neural network that exploit also wide kernels as an example where we would like to perform super resolution imaging. So let's say we start from a low resolution image and we would like to produce an high resolution one. In the output space, we have the output feature map that still consists of different channels. Now, in order to produce different output channels, we need to use different three-dimensional structure of kernels. These three-dimensional structures of kernels are called filters. So basically, the kernel in green, the kernel in orange, and the kernel in blue compose a three-dimensional filter in order to produce the activation of the output feature map. Now, we have just recalled some key concepts about convolution in order to understand what is happening under the hood. But we have to understand what are the, let's say, the gamers that stay in the game. So what are the metrics that we need to consider while dealing with convolutional neural network? As it is obvious, the first metrics that comes in our mind is the accuracy, so the quality of our prediction. Generally, the accuracy is based on the specific neural network model that we are using and the data that we provide to the network, that are the data set. Other metrics that relates to the specific composition of the convolutional neural network are the number of computation that the network has to perform in order to achieve a given task, and the number of weights kernel filters that we actually need in order to achieve that target. In this picture, we collect many representative convolutional neural network, and we consider as metric the accuracy, the number of computation in terms of flops, so floating point operations, and the size of the convolutional neural network in terms of weights parameters. In particular, the size is dictated by the size of the bubble. The larger the bubble, the more the parameters that the neural network needs to use in order to achieve the specific task. In this specific figure, obviously, the optimum area would be the area sitting at the top left, because our objective would be to achieve the highest possible accuracy by using a limited number of computation, because as an example, we would like to run a given task at runtime, and hopefully using a limited number of parameters, because anyway, we need to put these parameters somewhere before using and while using. So that would be the top area for our purposes. As you can see, we have plenty of, let's say, of architecture, starting from the AlexNet model that basically we might say is the open road model that show the promising involvement of convolution in the deep learning scenario. Why this? Because the convolution start gaining relevant attention starting from 2011, 2012, okay, when the deep learning era started actually in the AI domain. After that point, we had an explosion in the number of proposition of convolutional neural network, and this picture show some of them. Consider that it is dated back to 2018, this picture, but I would say the main message that should stay in your mind is that we need to consider the compromise between the accuracy that we can achieve and the number of computation and parameters that are required by the neural network. Just oh, sorry, I think there is a microphone open of someone. Anyway, and a final note, this top one accuracy refer to the ImageNet dataset. That is the art dataset for image classification. It consists of millions of images and 1,000 of classes to be detected. So it is a strong benchmark to consider in order to validate your model. But now, let's try to merge this basic concept that we got from convolutional neural network into the hardware implementation that we can do for them. So basically, we have two types of classes of compute architecture that might accommodate convolutional neural network. From one side, we have temporal architecture that you know well, so central processing unit, graphic processing unit, when we have a set of arithmetic logic unit that share control to a, let's say, top-level hierarchy and exploit single instruction, multiple data, single instruction, multiple thread in the case of GPU as an example, in terms of paradigm of sharing data. And on the other side, we have architecture that are developed in this space where the data may be shared between the arithmetic logic units. So the key difference is that in this special architecture, the data may be shared between the different modules that are responsible to do the computation. Another feature is that while in the temporal architecture, let's say the control and the buffering is generally managed at a centralized level, as you can see, in the spatial architecture, each specific arithmetic logic unit may accommodate their own control and local buffer facilities in order to improve also the capability to retain data close to the computational area. Systolic arrays are an example of spatial architectures. Now, why we need to stress the point to the fact to share data close to the computation? This stressing point comes from the energy demands that the different resources in a hardware architecture that is responsible to perform convolutional neural network, but more in general, AI, let's say algorithms, the energy demand between the different modules. And in particular, you may see that a simple 32-bit integer addition has a huge difference in terms of relative energy cost with a 32-bit DRAM memory access rate. The DRAM is the external memory that keeps your piece of information in order to be processed later by your core. As you can see, the difference between the addition and the DRAM accesses is higher than 1,000 of time in terms of relative energy cost. So if we do many readings to the external memory without finding a suitable way to buffer locally the data in order to enable sort of data reuse, this will impact significantly your energy demands. And so the overall energy efficiency or your architecture will be lowered. So this is the key motivation behind the use of systolic array in also everyday research. So the systolic array concept is quite old, so it is dated back to 1978, where Kung coined the term systolic array that basically is a class of parallel computing architecture arranged in this space where the data move synchronously by using some processing elements that, let's say, are interconnected with each other. As you can see in this example figure, we have data that may move horizontally, but also vertically. So each processing element is able to share the data with the neighborhood in two different directions. Now, between the 1978 to the emerging period of the deep learning, there was a sort of steady state of systolic arrays, so there wasn't so much interest in using them. But with the rise of the deep learning area, there was a boom in their usage. And I would say Google is probably the most representative character that effectively introduced their usage in the tensor processing unit. Just a side note, 2 days ago, it was presented, if I'm not wrong, the 7th generation of the tensor processing unit. So this highlights how systolic arrays are, let's say, actual and are interesting and useful in today's research, but not only research, but also for the industry development and management of architecture for AI models. And so basically in 2014, Google introduced the tensor processing unit that use systolic array to actually accelerate neural network computation. Now, according to the way in which data moves and the way in which a processing element may store locally a piece of information, as long as it is required, we might have different type of data flow stationarities. Wait stationary, output stationary, input stationary, row stationary. As an example, in a wait stationary systolic array, we load the weights, the kernels of the convolutional layer, and we save them at the processing element level as long as they need to be used. If you remember from the slides in which I was showing how a kernel scanned the image, basically we said the weights are shared for the entire feature map, no? So as an example, we may think that the set of weights is fixed at the processing element level, and they stay fixed until we process the entire feature map. So in this way, we are completely cutting some redundancy in memory access to the external memory to grab continuously the weights. The output stationary is another example. In the output stationary approach, we introduce an accumulator at the processing element level that continuously accumulates data. So we introduce sort of locality in the accumulation. On the contrary, the input stationary frees a portion of the feature map at the processing at the systolic array level, to be precise, until it is used. And finally, the row stationary, that is a more modern concept, is able to store different weights and different feature map values, feature map activation, usually arranged in rows, as long as they require. Now, for each type of stationarity, while the label, let's say, that identify the stationarity is kept fixed at the processing element level, the other type of data are moved across the array using the different orientation that the processing element offers. For example, in the weight stationary systolic array, while the weights are fixed, the other data moves, so the input activation and the partial sum may move using the different orientation. Now, how a convolution is actually distributed at the systolic array level. So basically, there are two types of approaches. One is to transforming the convolution in a sort of matrix multiplication that is most suitable for the systolic array data flow. And basically, this requires to reorganize the image and the kernel in a sort of Toeplitz matrix. So basically, each row of this matrix accommodate a window of the input feature map. As you can see, 1, 2, 3, 6, 7, 8, 11, 12, 13 are written in this row, and so on for the others sliding windows that scan the input feature map. What is the problem of this approach? We have a lot of redundancy. So basically, we need bigger memories to save data and to repeat the same piece of data multiple times. To be specific, the repetition in this image is highlighted by the red numbers. And as you can see, we have a considerable number of repetition. So definitely, this is degrading in terms of memory access because we will need to access more frequently and basically fetching the same piece of data different times. Another approach that has been proposed, let's say in 2015, 2016, is the row stationary, where Iris is the hardware architecture representing, let's say, the milestone architecture proposing the row stationary data flow. In this case, we don't need to, let's say, transform the input feature map in a Toeplitz matrix to, let's say, satisfy the general matrix multiplication, but we follow actually the raster scan order of the activation. And basically, each processing element, let's say, store a row of activation and a row of weights. In addition, we need to highlight that the same piece of information may be broadcast between different processing elements. As you can see, in the processing element 1, 0, the activation 6, 7, 8 are here, but also here. So basically there is a sort of diagonal broadcasting of the activation in order to, let's say, maximize the utilization and to allow to generate different results from different convolution at the same time. What is the drawback of this solution? In order to satisfy this type of data flow, we need to introduce at the processing element level some memory blocks that are usually in the form of scratch pads. So this will complicate the organization of the internal processing element. So other than, let's say, presenting a multiplier and then another, like in the weight stationary case, we have memory blocks that generally bring to a degradation in terms of power and energy, other than complicating the control that sit at the processing element level. So, considering this background, our objective was to find a suitable type of data flow and architecture able to reduce further the memory accesses to the external memory. And for this reason, we have TRIM, the triangular input movement systolic array. Now, the key features, the key aspect of this systolic array stays at the movement level. We enable different type of local connectivity between a processing element to the other in order to share data at multiple directions. Now, the composition of the different processing element is fairly straightforward. We have basically a multiplier, another, and few extra registers, and some multiplexer to identify, let's say, the path, the direction from which we receive the data. Now, let's try to briefly explain how the data flow works and then to see together an example. Now, first of all, we load the weights, so the kernels from the external. We load them vertically and we freeze them at the processing element level. So by this point of view, this reminds the weight stationary data flow, where we freeze the weights and we use them as long as they're required. The innovation stays in the movement of the activation, so of the pixel, let's say, of the input feature map. In particular, these weights follow a sort of triangular movement. We load them initially vertically from the external memory. Then we move as much as we can horizontally through right to left movement. And once we finish this movement, we reuse them as much as we can diagonally through the brown routes from bottom to top. So for this reason, we have a triangular movement: vertical, horizontal, diagonal. Finally, the partial sums moves vertically. At the bottom, there is an extra adder tree that is responsible to accumulate the final partial sum accumulation. Now, yeah, we have already introduced the processing element that basically consists of very simple multiplier and accumulator. And now let's try to understand how the data flow works, considering the same example of before, so a 5x5 input feature map and a 3x3 kernel. So first of all, we load vertically the data, so from the external memory, and they are subjected to a multiplication with the respective kernels. At the second step, the previous data are moved on the processing element that stay in the middle row, and they are accumulated to the new multiplication. So basically the computation that relates to the red box. At the same time, so in parallel, we have the starting of the computation of the second convolution. So we load from the, let's say, the external, the activation 4, while we reuse through right to left movement, the activation 3 and 2. Similarly, in the next cycle, we finalize, let's say, the first convolution. So basically, the bottom module are responsible to multiply the new activation 11, 12, 13, and summing up the results coming from the previous multiply accumulation. In the meantime, we continue the process of the second, let's say, sliding window in blue, and we are able to start the process of the third sliding window in green. So 3, 4, and 5. As you can see, while the, let's say, blue arrows refer to inputs loaded from the external memory, the other row refer to data reused from close processing element. In addition, we have some close registers that are responsible to prepare data to be reused for the diagonal movement. Finally, in the next stage, when we move to the new row of the input feature map, we finalize the diagonal movement. So basically, the activation that were stored in this register and in these two processing elements, so 6, 7, 8, are shifted at the top through the diagonal connection, so 6, 7, and 8. So we have reuse. So as you can see, in this cycle, from the external, we supply only these two pieces of data, while all the other data are reused locally. So we're reducing the number of external memory access to finalize the convolution. And so on till the completion of the algorithm. Now, as you can see, while we're progressing the computation, we're populating the output feature map area with all the pixels. And the type of movement is practically similar. So there is a, let's say, continuation of vertical readings and then reuse through right to left and diagonal movements till the completion of the computation. Now, while the example that we have shown in that picture was referring to a very toyful 5x5 feature maps, obviously this idea scale more in general for real feature map dimension. And in order to do so, what we have to do is to extend the size of the register that we were placing, let's say, on the left side of the systolic array. So instead of having a single register, we have a shift register buffer that depends on the feature map size and on the kernel size. The other type of movement is, on the contrary, is kept in the same way that we described it before. As you can see in the figure C, I have summarized the triangularity of the movement that give the name to TRIM, Triangular Input Movement Systolic Array. Now, while the architecture that we are showing here, that is generalized, this refers to a two-dimensional convolution between a single kernel and a single feature map. But as we said before, in order to manage complete convolutional layer for convolutional neural network, we need to have multiple feature map, multiple kernel, and an accumulation in this space. To do so, we conceived an hardware architecture that basically accommodate multiple primitive elements that we defined before, that we called trim slices. And these trim slices, the result from these trim slices are accumulated to an extra adder tree to finalize this space accumulation in order to get your output feature map results. In addition, in order to process in parallel more filters, so in order to being able to produce in parallel different output feature map, this type of architecture is arranged in a core format, and multiple core formats are stacked in a, let's say, top-level architecture with a further, let's say, buffering logic to process, let's say, the parallelism constraint that we have. So why this? Basically, when we process convolutional layers, we might have hundreds of feature maps and hundreds of filters. Obviously, we have some constraints that are dictated from the hardware area that we have. So basically, we have to schedule some operation in the time. So in the iteration number 1, maybe we're able to perform, let's say, 10 convolutions, and then in the iteration number 2, other 10 convolution. But what may happen is that the result from the convolution in the first iteration needs to be accumulated with the result of the convolution in the second iteration. So to do so, we need a sort of buffering logic that keep memory on what we generated in the first iteration. And it is the motivation of the output buffer that you can see in this picture. Now, in order to actually confirm the claim that we did at the beginning, in order to define a systolic array that was able to reduce the number of memory access, we did some comparison with the art. And in particular, we consider as a case study the iris systolic array that basically was related to the raw stationary data flow. So we're considering 2 different case scenarios. The VGG16 network, that basically is a convolutional neural network consisting of 13 convolutional layers and 3, let's say, dense layers. And each convolutional layer exploit 3 by 3 kernels. And we also consider the AlexNet model that is a bit older, but allow us to consider different kernel size, 11 by 11, 5 by 5, and then 3 by 3. As you can see, for the majority of the layer, actually trim exploit a very limited number of memory access. In particular, trim are the bars in orange, while the iris bar are in blue. And as you can see, for example, for the VGG16 network, we reach a reduction in terms of memory access of up to, let's say, 5.7 times, while for the AlexNet model, we reach even 8.26 times in terms of reduction in terms of memory accesses. So now this is an important consideration, and also it is proper to mentioning that the memory access that we report here are normalized memory access. So we're trying to take into account all the source of buffering facilities, so external memory, global buffer inside the chip, scratch pads for iris at the processing element level, but all the numbers are obviously referred to the external memory access in order to do proper normalization of the data. The results of these activities have been recently published in IEEE Transaction on Circuit and System 1. So using the DOI, you may access to the paper to investigate better also the more close hardware aspect, as an example, the implementation result, because we implemented this architecture on FPGA. But I would say the scope of today's talk is more to highlight the advantage in terms of memory access. But if you're curious to get more information, please feel free to have a look to the paper. Now, we said, okay, trim is responsible to reduce the number of memory access. But is there more to gain? So can we further reduce this number? And here we have a significant image that shows that in the current trim version, we still have a source of memory access overhead. So we still have to read again some feature map activation. And in particular, the issue stays at the border of the feature map. The border of the feature map, according to the movements of the data flow, needs to be read different time. And in particular, here we have reported that basically the smaller the feature map size and the higher this memory access overhead, so the number of extra time that we need to read the data again. So let's say our state-of-the-art work is trying to also solve this type of issue. And we had a proposition about this. In particular, we have introduced at the, let's say, buffer level, few extra registers that we call shadow register that are responsible to get rid of this overhead. So basically, the introduction of this shadow register are able to nullify this figure. Now, how this shadow register allow to do so? Here we have an example of an 8x8 input feature map, and I have highlighted in yellow the area of activation that needs to be read more than one time. So the area that unfortunately cannot be managed by the conventional trim data flow. And what happened is that we exploit the shadow register that are highlighted by these, let's say, boxes to store the activation that's there at the border. As an example, here we are referring to the process between the activation 6, 7, 8 till the activation 29, 30, and 31. And basically, as you may see, as long as we move through the clock cycle, the border activation are stored at that level. Once we store the target activation that needs to be reused at some point, we freeze those registers, so we don't allow any further readings, and we keep the data until they need to be used. In particular, we highlight in yellow this type of data reuse. With this approach, we are able to completely get rid of this problem. Now, in this same round of research, other than proposing this, let's say, type of buffer that we call input recycling buffer, we also tried a bit the layout of the architecture. In particular, we moved from a, let's say, standard trim module to a three-dimensional trim module. In particular, now we have different cores that accommodate different trim slices. And here, each slice shared an input recycling buffer. So basically what happened at the core level is that we provide one input feature map, and basically each slice accommodate a different filter to generate multiple output feature map from the same core. Now, in order to accommodate this type of data reorganization, we need to add extra other trees that basically are shared between multiple copies of core. So enabling a sort of three-dimensional shaping of the other tree. This three-dimensional shaping gives the name to 3D trim. And as I told you, the input recycling buffer is the new, let's say, local buffering facilities that accommodate the previous shift register buffer, as well the shadow registers. Now, in order to understand if we actually, let's say, got the point to reduce the memory accesses, we consider the same previous convolutional neural networks, so VGG16 and AlexNet, and we did a comparison in terms of operation per memory access per slice between the previous stream and the three-dimensional version. As you can see, for both the case, we have a reduction of memory access of, let's say, 3 times in the VGG16 scenario, and also up to 3 times in the AlexNet perspective. Now, this is what we have currently done. This paper is, the preprint is currently available on arXiv, while the actual version is under review to the IEEE. Now, today, what we did, I'm approaching to the conclusion of the talk, we tried to provide sort of context about the significance of convolutional neural network and how they may be actually implemented in hardware by proposing an innovative type of systolic array that exploits a triangular input movement. What are the, let's say, key takeaways of today's discussion? So what it is worthy to remind? First of all, we said convolutional neural network extract features from images of different level of abstraction. We start from, let's say, very basics, edge shapes, And progressively we built complex object colors. So in a way or in another, we are mimicking the human visual system. So starting from the retina, we move towards the visual cortex and finally to the inferotemporal cortex to actually finalize the recognition of the pattern. But we said what we have always to keep in mind when dealing with convolution is obviously the accuracy to reach a given target, but also the compromise with the number of operations and the memory requirements to save the set of parameters that allow you to do the real learning. So definitely we have demonstrated that systolic arrays are suitable, let's say, to fit this compromise, especially in terms of memory access, that usually literature is defined as the von Neumann bottleneck, no? So the frequent communication between the computing core and the memory. And thus we have TRIM, a new type of data flow and systolic array that exploit input feature map utilization maximization through local triangular movement, and as a key result, reduced memory access when compared to the art and to some state-of-the-art convolutional neural networks. So I hope that, let's say, at the big lines, the idea was clear enough. And so this is the end of the presentation. Thank you all for listening, and I'm here for your questions.